Goal of Lab 5 is to design and test a single port RAM which has 16 memory locations where each location can store up to 8-bit wide data. A single port RAM has 4 ports, 3 inputs, address, write enable, and 1 in-out port, data, which is 8-bit wide. If we want to perform a write operation, the spec says write enable should be high and enable should be low. To perform a read operation, write enable should be low and enable signal should be high. Now let's see how this is coded in the RTL file. We declare the ports and direction at the start of the RAM module. Then we declare an array which is 16 location deep and 8-bit wide. This will be our memory. Let's go over the syntax to declare an array. Here first we declare the type, which is reg, then how wide each location is going to be, which is 7 down to 0, 8-bit. After that the name of the array is followed by the depth, which is 16. We will see how to perform a write operation. In the sensitivity list of the always block, we have data, write enable, and address, which are the control and data signals to the block. If write enable is high, enable is low, that is not of enable, store the data into the location driven on the address pin of the memory array. So the data is written into the location driven on the address. To perform the read, we use a ternary operator. Now the condition for read is enable should be high and write enable should be low. If that happens, then the value which is present in the memory location shown by the address is driven into the data. Else Z is driven on the data lines. Now let's go over the test bench. At the start, we declare the variables that will be required to drive the inputs and receive the outputs from the DUT. Then we declare the internal variables that will be required to generate the stimulus, that is temp D and integer L. Thereafter, instantiate the design with implicit or explicit port connection. Here we have used implicit connection, but the recommended way is to use explicit as they are less prone to errors. Then we write a logic to drive the data on the data pin when the write operation is going on and drive Z during the read operation. Task initialize is used to initialize all the input, and simulus is used to assign the address and temp value which will be given to it as the input. Write and read task will assign appropriate values to WE and enable for their respective operations. Delay task is used to add delay during the execution. In the initial block, we first initialize the inputs, add a delay, and then configure the DUT for the write operations. Then we go ahead and write in all the locations using a for loop. Similarly, read operation is performed on the DUT after configuring it for read using a for loop. Finish is used to end the test. Let's compile and simulate the design. Click on File, New, Project. We'll name this project as RAM and select the project location as Sim. Add the existing files. We'll add the RTL file and the TB file. And select compile all. The compilation is done. As we can see, the tick marks. Simulate, start simulation, and we will select the RAM TB, click OK. design is loaded. Right click, add to wave, all items in the region and below. Let's go back to the wave window. Here we will look at the TB signals and delete the rest of them and run all. Click on no. Let's go back to the wave and zoom full. For the ease of reading, we will select both of this, right click on it, select the radix as unsigned. Initially, as we have in the test bench, we do all the writes and then we do all the reads. So here we are writing 0 in the 0th location, 1 in the first location, 2 in the second, and so on till 15. And when the WE is low and enable is high, the read operation starts. And we can see that when we are trying to read, we get the same data out. When we read the 0th address, we get 0, 1, 1, 2, and similarly till 15. Now we have completed the 5th lab. In the lab 6, we will get familiar with the FSM design. For this lab, we will design and test a sequence detector, which detects 101 at the input stream. As shown in the block diagram, D-in, reset and clock are the inputs and D-out is the output. On the right hand side, we have the FSM